Section 11.4 covers the topics of absolute convergence and alternating series. An alternating series is just a series in which the sign of each term of the series alternates between positive and negative. So you can see here in example 1, we have an example of an alternating harmonic series. What you will frequently see in a series that is going to alternate is some sort of negative base number, because negative numbers, when you raise them to even powers, become positive, but odd powers, they stay negative. So that'll create this series of alternating signs that you see in this particular series. And we're asked to determine, is this going to converge or diverge, and then estimate the limit. So if we think about the partial sums here, S sub 1 would just be the first term, 1. S sub 2 would be 1, but then the next term is to add a negative 1/2 or subtract 1/2, and now we're back down to 0.5. So in the third term, we're going to be adding a fraction on, so we're going to make it a little bit bigger. But then in the fourth term, we're going to be subtracting something. So you can see how we're taking a couple of steps forward and a couple of steps back as we continue to write out the partial sums for this particular series. Let's go ahead and look at a lot more terms in Mathematica. I've stored a function to create my partial sums, and here's a table of values set to go from 1 to 1000 in steps of 50. So what appears to be happening is that this series is going to converge. It looks like it's hovering around 0.69. So I would say it converges to approximately 0.69. But not all alternating series will converge. We can compare it with the regular harmonic series, which is the same as the one above, except now the signs no longer alternate. And this is easily shown to diverge using the integral test. If we just compare that to the improper integral of 1 over x dx, it would be very easy to integrate this integral and show that it diverges. So the only difference between these two series, or another way to think about this, is I can generate the regular harmonic series from the alternating one if I go ahead and take the absolute value of every single term. If I do that, the positive terms stay positive, but the negative terms will switch signs and become positive. So the connection between these two is that the absolute value of this series gives us this series. Now we're going to look at that link between a series and its absolute value a little bit more closely in this next example. For instance, my original series here is the series k equals 1 to infinity of sine of k over k squared. And if I were to take the absolute value of my a sub k, that would give me the series k equals 1 to infinity. Sine obviously can take on negative values. It's going to bounce between +1 and -1. So I would want to keep the absolute values around that numerator. However, in the denominator, the absolute value of k squared, well, k squared is going to be a positive number always. So I can just drop those absolute value bars, and you can see that we did create this second series by taking the absolute value of the first. Now let's take a look at the behavior of each of these series using Mathematica. I've asked Mathematica this time to show me the plot of the partial sums. This is for the original series without the absolute value in it. And you get this cool graph. And if I increase my range of n values, you get an even cooler looking graph. But clearly, these partial sums do seem to be converging to a number somewhere around this 1.01396. Now I can go back up and put in absolute value bars around the numerator. restore that function. And here's what the absolute value partial sums look like. In this case, you can see it does appear that they are also converging, much different behavior in terms of we're not seeing positives and negatives, of course, because we put the absolute value in there, everything is positive. And we're converging to some number a little bit higher than 1.278. So as you can see, I've recorded the values that each of these series converges to. I've listed the limit of the partial sums as approximate values. The other interesting thing that's happening here is when we take the absolute value of the series, we have created a non-negative series, which was the subject of the last section where we looked at different tests for non-negative series. And the first of those was actually the comparison test. And the comparison test said that if you can establish a series to compare your series with, then depending on their relationship, which one's bigger or smaller, you can determine if one or the other converges or diverges. You can show by looking at the partial sums that this simplified version of our series based on 1 over k squared, that series is going to converge. And since we have a non-negative bigger than 0 series in the form of absolute value sine of k over k squared, and that's always going to be smaller than just 1 over k squared. Since we know that this one converges by the comparison test, this one must converge as well. So that's how you would actually go through and justify the conclusions that we reached by looking at the limits of the partial sums. This brings us to the idea of absolute and conditional convergence. If you have a series based on a sub k, if the series where you take the absolute value of those terms converges, then we say the original series converges absolutely. If it turns out you take the absolute value of the terms and that series diverges, but your original series does in fact converge, then we say that the original series converges conditionally. So absolute convergence is a stronger form of convergence because not only does the original series converge, but so does its absolute value. Whereas in conditional convergence, the absolute value diverges, but the original series converges. And related to that, if we have a series and its absolute value converges, then so does the original series, which we already knew that from above. But more specifically, we can relate the values that they converge to by this inequality. Let's go ahead and apply that theorem to example 2. So in example 2 that we were just looking at, it was the original series without the absolute value. And based on this new terminology, we have shown that this one converges absolutely, because not only does it converge, but so does the series based on its absolute value. So because this one converges absolutely, we can apply this theorem. I went ahead and substituted my a sub k into both sides of this inequality. We showed that the original series converged to a value of approximately 1.014. And of course, if we take the absolute value of that, we have still 1.014. And this theorem says that that value should be smaller than the convergence that we got for the absolute series, and that we got approximately 1.28. So that's just one example of the theorem